Hi, so in this lesson, we're going to look into buffers in action. I have three examples that I'm going to go through with you, and what all three examples have in common is that they're all about calculating pHs of buffers. So, in the lesson regarding what buffer is, we already know how buffer buffs and how to make one. Okay, so we made an acidic buffer, we made a basic buffer. All in all, the whole idea of buffer is that when you have a buffer solution, and if somebody were to add acid or base, especially strong ones, the pH won't change so much because they'll have conjugate base to sort of pick up the acid, and they'll have conjugate acid picking up the extra base. So we know that works. We know that happens. But what we don't know is how pH will change when you add a little bit of acid into a buffer or a little bit of base into the buffer. So in this lesson, we're gonna do that. Okay? So let's start with an example here. I have a buffer. It's an acidic buffer. Okay? Made up of 20 milliliter of 0.1 carbonic acid and 10 milliliter of 0.1, now that's of course molarity, of sodium bicarbonate. Okay, so obviously this is the weak acid and this is its conjugate base. If you remember from last time, to make a buffer, half of the conjugate base of a weak acid will get you a buffer. Okay, by graphing it, okay, by doing a titration curve, which looks like this, it will end up being at this region, and that is what we call the buffer region. Now, let's start off with looking at this question. I have this buffer. What is the pH of this buffer? Okay, let's take a look at how we can find that out. Now, I'm going to show you two methods. The first method is what makes sense. Second method is really just plugging number into an equation, but you will get the same answer. Obviously, the equation one, which I will call method 2, is the one that most people will use because it's fast, it's easy, but it really doesn't tell you why you're doing certain things. But however, the first method, hopefully it makes sense. So, how do I find the pH of this buffer? First, I need to know a couple of things. This is what's inside your flask, okay? And I want to know two things. What is the concentration of carbonic acid? And what is the concentration of sodium bicarbonate? Okay, so to do this is very simple, just very simple molar calculation. So I have to start with right here 0.1 moles per liter of carbonic acid, and I have 20 milliliters of it. This will give me how many mole of this there is in the beaker. Okay? And then I'm going to divide this by the total volume. By doing that, I now have the concentration, the final concentration of H2CO3. And the answer here is 0.0667 in molarity. Okay, let me just move this down a little bit. Okay, that way it's not taking up so much spots. Okay, there you go. So I will do the same thing with sodium bicarbonate. What is the final concentration of that? So I started out with 0.1 molar of this with only 10 milliliter because I just want half. So, and then I'm going to divide that by the total volume. And the concentration here is 0.0333. All right, So now that I know the final concentration of both of my chemicals that makes up my buffer, I now want to know what is the H plus concentration of this. Now it has to be H plus concentration of this. The reason is very simple. There's obviously way more of the acid than its conjugate base. What that means is that if these guys were to exist together, there's obviously a chance here that this is going to be in excess. This is going to be in excess. The question is, how much in excess? So we're going to do a reaction. Okay, we're going to look at the dissociation of carbonic acid. Okay, where it creates H3O plus and HCO3 minus. Okay, so if you think about it, inside this beaker right here, we have a concentration of 0.0667 of carbonic acid. Okay, this guy never play a role. And let's say we don't have any of these, at least not yet. But do we have any of these? Yes, we do. Sodium bicarbonate obviously will break up into sodium plus and bicarbonate anion. So we do have bicarbonate here. So in terms of bicarbonate, the final concentration here is 0.0333. Okay, so let's do a nice table. In terms of change, you're going to get less and less of this, and you're going to get more and more of that. Okay, because that's what H2CO3 does. And here, of course, we will look at equilibrium. This is how much we have left. So as we added, as these guys mix together, okay, this will be less and less and less. Okay, whereas actually this will get more and more and more. You have this to start with. Okay, so every time when this dissociate, as you see here, you're going to get more of these guys. And of course, having more of these, meaning that you'll have less of these. So that's the idea here when you put these together. All right. Hey, just to let you know, carbonic acid has a dissociation constant here of 4.47 times 10 to the power of negative 7. Okay, I looked that up earlier, so we can put this into our Ka expression. So Ka is equal to X, okay, times 0.0. Well, let me just write out the expression. So I have here H3O plus times HCO3 minus all over H2CO3. Okay, in that case, we're looking at 4.47 times 10 to the power of negative 7 is equal to X times 0.0333 plus X divided by 0.0667 minus X. Now, hopefully you have heard of 100 rule. Okay, if you heard of 100 rule, apply 100 rule, and you'll notice that this and this will be gone. Okay, remember, only if you know your 100 rule. By doing that, you escape that lousy quadratic equation that everybody want to escape from. And now we know that X is equal to 8.95 times 10 to the power of negative 7. Okay, so what is X? X is the concentration of H3O plus at equilibrium. So what that means is that I can directly calculate pH. So pH is equal to the negative log of 8.95 times 10 to the power of negative 7, because that's how you find pH is the negative log of H3O at equilibrium. So that will be 6.05. 0.05. So the pH of this buffer is 6.05. It's slightly acidic. Now that's not surprising because if you look at how we made it, the concentration of the weak acid and its conjugate base is the same, but we have more of the weak acid, so it's not surprising, of course, that the pH is slightly acidic. Okay, so all acidic buffers have pH less than 7. Now it's not going to be very low, that's for sure. It's going to be, usually buffers are in between 5 to 9. We call that good buffers. And for this one, a carbonic acid buffer at 6.05 is absolutely fair. All right, so that's how you calculate pH of buffers. Now, I'm going to do it another way. I'm going to look at it in another method. This method is, I guess, more widely used. You'll see more textbook using this. But why they use this, they don't say much about. Hopefully you understand how we calculate a pH through the idea of final concentration. And having this as an access, we were able to derive a nice table to calculate H3O plus at equilibrium. All right, so let me erase all of this. I'm going to do this question again. But this time, I'm just going to use an equation. This equation is called the Henderson-Hasselbalch equation. It looks like this, where pH of a buffer is equal to pKa plus the log of base over acid. Now, base on acid can be in molarity, or you could be looking at it in mole. The reason is very simple. It's because both acid and its conjugate base is in the same beaker. So the volume, the overall volume here, moles per liter, the liter is really the same. Because if the liter is the same, you can just cross them out. So you can have these as concentration molarity, or you can just use mole. I like to use mole. Makes more sense than putting molarity. But I'll do both. I'll do moles. All right. Hopefully you remember what that answer was. Okay, I think the answer was 6.05. So let's see if we still get 6.05 as our pH. So let's go. pH is equal to pKa. P means negative log, so we're going to negative log this. Okay. Now if you think about it, this as a buffer, this makes sense because for at buffer region, pH actually equals to pKa. That is when these two are the same. When these two are the same, it will be 1. Log of 1, of course, is 0. But we're not here to look at math in terms of how great it is, because I don't want you guys to vomit. Plus log. Now, base. Okay, this is the base. So I'm going to put 0.1 moles per liter times 0.01 liters. This will give me the mole of the base, divided by the mole of the acid. So this will be 0.1 moles per liter times 0.02 liter. Okay. Now, if you were to put in molarity for the top and bottom, be careful here, okay? A lot of people would put, oh yeah, this is the acid. I'm going to put 0.1 here. This is the base. I'm going to put 0.1 here. But no. Don't do that. These are the original concentration. What's going here and here are final concentration. So make sure if you were to put molarity here, you do this, and then you divide it by 0.03. You do this, you divide it by 0.03. But there's really no point of doing that to the top and bottom, so that's why we decided to look at mole here and look at mole here, because that would be enough. Now, if you were to put all of these into your calculator, because you love your calculator, this negative log of 4.47 times 10 to the power of negative 7 is 6.35. Okay, the log of this mess right here is negative 0.3. And wow, you get the same number with what, a quarter of the work? Now, the Henderson-Hasselbalch equation is a very, very useful equation, very famous equation, used strictly to calculate pH of buffers. Hey, feel free to use it, but also make sure you know method 1, okay, in terms of why it is 6.05, and not just, plug numbers into an equation, evaluate, and not knowing exactly why that is. That's pretty dangerous. All right, let's continue. Okay, let me just erase all of this. Okay, so I'm going to keep the buffer. This is my buffer. I'm going to keep my pKa as well. I'm going to put a cloud on it. Okay, to let everybody know we're using the same buffer for the next reaction. So, let's take a look at this example. I am going to do this. I am going to add 5 milliliter of 0.1 molar HCl to this buffer. Okay, so I have a flask. Inside this flask, I have this buffer that I made. Okay, beautiful buffer that I made. And for some reason, I decided to add some of this stuff in here. Okay, the whole idea of buffer is to maintain the pH to be stable. That's why we add buffer to things, so pH don't change even though somebody were to dump some strong acid in there. Okay, because what's happening here is that this guy will start to come to play. The conjugate base here will say, hey, acid, what are you trying to do, huh? Trying to mess us up? Well, you know what? I'm going to neutralize you. That's what's happening. But of course, our goal is to find out what is the pH when all of this are combined. All right. Let's use Henderson-Hasselbalch equation, because that's the fastest way and most accurate way of calculating things. But be careful in terms of what you do, okay? Make sure you understand exactly what you're doing. So here's Henderson-Hasselbalch equation. Okay, so first I'm going to negative log my pKa, which is the dissociation constant of my buffer, plus I'm going to log my base, 0.1 times 0.02. Okay, oh, I think I'm looking at the wrong column. 0.01, that's the base, over 0.1 times 0.02. Extend this, because this, yes, is the original constant, it's the original mole of my base. This is the original mole of my weak acid. However, after adding these, after adding 5 milliliter of HCl, which is a strong acid, I can tell you right now that the final concentration of base and the final concentration of acid is not the same anymore. Now, think about this. Think about this. You're adding acid in here. What the acid is going to do is that it will react with your conjugate base. So if your acid is reacting with the conjugate base, what that means is that some of these are going to be reacted and gone. So what that means is that the numerator right here will actually be less. How less? I don't know. Let's put a minus here for the sake of knowing that we're going to subtract whatever mole that is here. Now, hopefully you understand this. What about acid? Well, if we are reacting some of these, obviously we're adding to these. So I'm going to put a plus here. How much are we going to subtract and how much we're going to add? Obviously, is determined by how much acid did you add. So in terms of mole, this is going to be 0.1 moles per liter, and I'm adding 0.005 of it. Okay? And the same right here. Okay? So my original base mole of my buffer minus the mole of acid I am adding. The original mole of my weak acid adding to whatever mole of acid I'm adding. Okay? Now, once you do that, you're going to have 6.35 plus log of 0.0005 divided by 0.0025, and your answer here is going to be 5.65. Which is pretty good if you think about it. Before you added the acid, the pH was 6.05. Oops. The pH was 6.05. By adding 5 milliliter of this very strong acid with pretty much the same concentration, that didn't actually drop the pH that much. It dropped it by maybe like 0.4, 0.5. Okay, so that's the power of the buffer. Even if you were to add some really strong acid, which is lots of H, these lots of H's are not going to be overtaken what's already in here. Okay, so the pH of the solution is actually 5.65. Now, hopefully you know exactly what I did right here, why we subtract the base and why we add the mole of acid. Okay, let's clear this up and let's do one more question. Hopefully, maybe I shouldn't have erased all of this. Okay, I am now gonna add instead. Let's see. Let me add 10 milliliter of 0.1 molar NaOH. Okay, so again, I have my buffer. This time, I'm going to add a strong base in there to see if this number is going to change. Now, when we add acid there, it became a little bit more acidic. I'm sure if we were going to add a base in here, this thing is going to get a bit, I wouldn't say a bit basic, but less acidic. All right, that's the word that I was looking for. I'm not going to make this solution basic. I'm going to make this less acidic. Okay. All right. So again, same idea. In this case, what is the pH when I add all of these things together? All right, Mr. Henderson Hasselbalch, show me your face. pKa is plus log of base divided by acid. Okay, so pH is equal to the negative log. I really shouldn't erase this I really should just keep it here since I'm going to write it so many times. Plus log. Okay. What would this be? Let me write this smaller because I'm going to be running out of room and okay, 4.47 times 10 to the power of negative 7 plus log of the base. All right, so the base was 0.1 times 0.01, and the acid was 0.1 times 0.02. Now, let's go. Earlier, we subtract and we add. Is that still going to be the same? We added base in here. What is the base going to do? The base is going to react with the acid this time. Okay? Since the acid is being reacted by the base, then the acid is the one that will be subtracting. Because there's going to be less of these, because these guys are saying, hello, acid, let's react. So that's why the denominator here is going to be less. Because you're adding a base, there'll be more base. See the idea of Hall reverse. So we're going to put in the number of base, mole of NaOH here and here. Okay, so make sure you know why this is plus and why this is minus. And by doing that, you're going to get 6.35 plus log of 0.002 over 0.001. And your final answer here is true. It is less acidic, not basic, not supposed to be. The buffer, okay, will just change to something less acidic because you added some strong base in there. Makes sense. But obviously, this pH is not going to shoot all the way up to higher than 7. It will, I guess, if you were to put a lot of these. There's no such thing as a buffer that will buff forever and buff really crazily. Okay, but that's the idea here. Okay, so the whole point of this lesson is to first look at what is the pH of the buffer. Number 2, if I would add a little bit of strong acid to my buffer, how would the pH change? And number 3, if I were to add a little bit of the base, strong base, what would the change of the pH be as well? All right, so hopefully you guys understand all of this. All right, bye.